Distinguished external and internal examiners, supervisors, academic colleagues, industry experts, and viewers joining this presentation, welcome. My name is Ibrahim Adabara. This presentation summarizes my PhD research titled Development of a Framework for Ethical Governance and Cybersecurity Resilience in Healthcare Systems based on Agentic Artificial Intelligence. Before the formal presentation begins, let us start with a short scenario. Imagine a hospital on a busy morning. Doctors are accessing electronic health records. Nurses are monitoring patients through connected medical devices. Laboratory results are moving digitally from one unit to another. Telemedicine systems are supporting remote consultations. Everything depends on digital connectivity. Now imagine that, in the middle of this activity, the hospital system detects unusual network behavior. It may be a cyber attack. At that moment, the question is not only this: can the system detect the attack? The deeper and more important question is this: how should the system respond without disrupting patient care, violating privacy, or making an unsafe automated decision? Should it block the device immediately? Should it isolate part of the network? Should it alert a human expert? Or should it continue monitoring before taking action? This scenario captures the central challenge addressed in this research. The study developed an Agentic Artificial Intelligence framework, abbreviated as AAIF. AAIF is designed to support healthcare cybersecurity systems that are not only intelligent and adaptive, but also ethical, explainable, accountable, and governed. That is the focus of this presentation. This research was carried out under the academic guidance of a distinguished supervisory team. The main supervisor was Associate Professor Bashir Oleniyi Sadiq. The co-supervisors were Associate Professor Aliyu Nuhu Shuaibu, Associate Professor Yeldan Ibrahim, and Associate Professor Maninti Venkateswalu. Sincere appreciation is extended to them for their guidance, critical feedback, encouragement, and support throughout this PhD journey. Their supervision helped shape the conceptual direction, methodological rigor, technical development, and final quality of this research. This presentation is organized into 5 main parts. First, it presents the research background and problem. Second, it discusses the literature review and research gaps. Third, it explains the methodology and framework development. Fourth, it presents the results and discussion. Finally, it discusses the contributions, conclusion, recommendations, limitations, future work, publications, and references. As the presentation progresses, one central idea should remain clear. Healthcare cybersecurity should not only be technically strong. It should also be ethical, accountable, explainable, and resilient. This is the central message of the thesis. Healthcare systems are becoming increasingly digital. Hospitals now depend on electronic health records, telemedicine platforms, connected medical devices, cloud-based systems, and Internet of Medical Things technologies. These technologies improve healthcare delivery. They make patient records easier to access. They support remote care. They improve clinical coordination. However, they also increase cybersecurity risks. Globally, cybercrime has become a major economic and institutional threat. Cybercrime costs were projected to reach about $10.5 trillion United States dollars annually by 2025. This shows that cyber insecurity is no longer a minor technical problem. It is now a global resilience challenge. In healthcare, the risk is even more serious. When a hospital system is attacked, the problem is not only stolen data. The attack can affect patient safety. It can delay clinical services. It can compromise connected medical devices. It can also reduce public trust in healthcare institutions. This concern is especially important in developing regions, where digital health systems are expanding faster than cybersecurity and governance capacity. For example, mobile internet penetration in sub-Saharan Africa reached about 27% by the end of 2023. This shows that digital connectivity is growing. But as connectivity grows, healthcare institutions also face a wider cyber attack surface. Traditional cybersecurity systems are often reactive. They detect known threats and respond based on predefined roles. However, healthcare environments require more than reactive defense. They require systems that can adapt to changing threats. They require systems that can explain their actions. They require systems that can respect patient safety. They also require systems that can operate within ethical and regulatory boundaries. This is where agentic artificial intelligence becomes important. Agentic AI allows intelligent systems to perceive their environment, reason about possible actions, learn from feedback, and act toward defined goals. In this study, this idea is applied to healthcare cybersecurity through the development of the Agentic Artificial Intelligence Framework, abbreviated as AAIF. The key message from this slide is simple. Healthcare cybersecurity is no longer only a technical issue. It is also an ethical, governance, and resilience issue. The problem addressed in this study is the absence of an integrated framework that combines four important dimensions: adaptive intelligence, ethical reasoning, governance compliance, and healthcare cybersecurity resilience. The seriousness of this problem is supported by global cybersecurity data. Healthcare organizations have become major targets for cyber attacks. In 2022, healthcare organizations experienced an average of about 1,426 attacks per week. More recent reporting showed continued escalation, with healthcare organizations experiencing approximately 1,999 attacks per organization per week in Q2 2024. Healthcare also remains one of the most expensive sectors for data breaches. The average cost of a healthcare data breach was reported at about $9.77 million United States dollars. These figures show that healthcare cybersecurity is not only a technical concern. It is also a patient safety, financial, institutional, and governance concern. Many existing AI-based cybersecurity systems focus mainly on detection accuracy. They may answer one question: is this traffic normal or abnormal? But in healthcare, more questions must be asked. Is the response safe for patients? Is the decision explainable? Does it respect privacy? Does it comply with institutional and regulatory requirements? Can a human expert review or override the decision when necessary? This is where the research gap becomes clear. A system may detect an attack accurately, but if it cannot explain its decision, if it cannot respect governance rules, or if it takes an unsafe automated action, then it may not be suitable for healthcare. For a non-technical audience, this point can be explained simply. A cybersecurity system in healthcare should not behave like a black box that makes decisions without explanation. It should behave more like a responsible assistant. It should detect threats. It should check the rules. It should consider patient safety. It should explain its decision. And it should escalate to human experts when required. Therefore, the core problem is that many current AI-based cybersecurity approaches lack ethical reasoning, governance alignment, interpretability, and healthcare-specific contextual awareness. This study addresses that problem by developing AAIF as a governance-embedded and ethically aligned framework for healthcare cybersecurity resilience. The main objective of this study was to develop an agentic artificial intelligence framework that integrates ethical governance, interpretability, cybersecurity resilience, and policy compliance into autonomous healthcare cybersecurity systems. The study was guided by 6 specific objectives. The first objective was to identify and define the functional, ethical, and governance requirements for an agentic AI cybersecurity framework in healthcare systems. The second objective was to design a conceptual framework integrating agentic AI, ethical reasoning, and cybersecurity governance. The third objective was to develop the AAIF architecture for autonomous intrusion detection and context-aware response. The fourth objective was to simulate adversarial and cross-domain cybersecurity scenarios within a healthcare-oriented environment. The fifth objective was to evaluate AAIF using multi-criteria metrics, including cybersecurity effectiveness, ethical compliance, governance alignment, and interpretability. The sixth objective was to validate the applicability, robustness, and scalability of AAIF in resource-constrained healthcare environments. Therefore, the study followed a clear pathway: requirement identification, conceptual design, architecture development, simulation, evaluation, and validation. This structure ensured that the research moved logically from problem identification to framework development and then to testing. The main research question asked, how can an agentic artificial intelligence framework be developed to enable ethically governed, adaptive, and resilient cybersecurity in healthcare systems? And how can its effectiveness be evaluated in resource-constrained environments? The specific research questions were aligned with the 6 objectives. They focused on identifying the requirements, structuring the framework, operationalizing governance principles, testing adversarial response, selecting responsible evaluation metrics, and validating robustness and scalability. The logic of the research questions can be explained in 6 simple steps. The first question asks, what is needed? The second asks, how should the framework be designed? The third asks, how can governance be built into the system? The fourth asks, how does the framework behave under cyber attack scenarios? The fifth asks, how should performance be measured responsibly? The sixth asks, can the framework remain useful in resource-constrained healthcare environments? These questions guided the entire study. They ensured that the research remained focused, measurable, and aligned with the problem. The scope of this study is healthcare cybersecurity and AI governance. The study focused on the design and simulation-based validation of AAIF. It did not involve live hospital deployment. This is important because healthcare environments are sensitive. Using real patient data would introduce ethical and privacy risks. Instead, the study used public benchmark cybersecurity datasets and a simulated healthcare environment inspired by KIUTHR. The datasets included CSET 2017, CSE, CIC, IDS 2018, and Adabara 6.2. One important clarification is necessary. The datasets are public cybersecurity benchmark datasets. The healthcare relevance comes from how the study contextualized and simulated the framework within a healthcare-oriented environment. The geographical and contextual focus was the Ugandan healthcare environment, especially resource-constrained healthcare settings. Therefore, the boundary of the study is clear. This was not a live hospital implementation. It was a controlled, ethical, simulation-based study. The purpose was to test whether an agentic AI framework can improve cybersecurity resilience while maintaining governance and ethical accountability. This study is significant in 4 main ways. First, it has theoretical significance. It contributes to agentic AI by showing how autonomy, adaptability, ethical reasoning, and governance can be integrated into one cybersecurity framework. Second, it has governance significance. It demonstrates how principles from NIST Cybersecurity Framework 2.0, HIPAA, and ethical AI can be operationalized inside cybersecurity decision-making. In this study, HIPAA is used as a mature healthcare security and privacy reference standard. The healthcare context remains grounded in the Ugandan and KIUTHR-inspired environment. Third, the study has practical significance. It provides a framework that can guide healthcare institutions, particularly in low-resource settings, toward more accountable and resilient cybersecurity systems. Fourth, it has trust significance. In healthcare, users need to trust intelligent systems. Trust requires more than accuracy. It requires transparency. It requires accountability. It requires explainability. The key message from this slide is that AAIF is designed to make AI-based cybersecurity more trustworthy, more responsible, and more suitable for healthcare environments. This study is grounded in 3 main theories. The first is agent theory. Agent theory explains how intelligent agents can perceive their environment, reason about situations, and take action towards specific goals. In this study, agent theory supports the autonomous behavior of AAIF. It explains how the framework can observe cybersecurity conditions, interpret risk, and select appropriate actions. The second theory is reinforcement learning. Reinforcement learning explains how an intelligent system can learn from feedback and improve its decisions over time. This is important in cybersecurity because threats are dynamic. Attack patterns change. System conditions change. And defensive responses must also adapt. The third theory is machine ethics. Machine ethics explains how ethical reasoning can be embedded into artificial systems. This helps ensure that system decisions remain safe, responsible, accountable, and aligned with human values. For a non-technical audience, the three theories can be understood in a simple way. Agent theory gives the system independence. Reinforcement learning gives the system adaptability. Machine ethics gives the system responsibility. Together, these theories support the design of AAIF as an autonomous, adaptive, and ethically governed cybersecurity framework. This slide presents major artificial intelligence techniques used in cybersecurity. Machine learning is commonly used to detect patterns and classify normal or abnormal behavior. Deep learning is useful for analyzing complex and high-dimensional data. Reinforcement learning supports adaptive response by allowing systems to learn from feedback. Natural language processing can support threat intelligence by analyzing security reports, alerts, logs, and text-based information. Graph-based techniques can model relationships between devices, users, systems, and network activities. These techniques are useful. However, the main argument of this study is that AI techniques alone are not enough for healthcare cybersecurity. A system may be technically accurate, but it may still be unsafe if it cannot explain its decision. It may still be unsuitable if it does not respect privacy. It may still be risky if it cannot follow governance rules. Therefore, this study does not only ask how AI can detect threats. It asks how AI can detect and respond to threats responsibly. That is why AAIF integrates intelligence with ethics, governance, and resilience. Conventional AI is usually task-specific. It may detect an intrusion. It may classify a threat. It may predict an anomaly based on previous training. Agentic AI goes further. It can reason. It can adapt. It can pursue goals. It can interact with its environment. And it can take action within defined boundaries. A simple example helps explain the difference. A conventional AI system may say, "This network traffic is suspicious." An agentic AI system may respond differently. It may say, "This network traffic is suspicious. The risk should be assessed. The proposed response should be checked against policy. The possible impact on patient services should be considered. The decision should be explained. And if necessary, the case should be escalated to a human expert." That difference is very important in healthcare. Healthcare cybersecurity decisions must not only be fast. They must also be safe. They must be explainable. They must be accountable. This is why the agentic AI approach is central to this research. This slide presents the conceptual framework of the study. At the top are the policy and governance sources. These include NIST Cybersecurity Framework 2.0, HIPAA, and ethical AI principles. These sources feed into what this study refers to as the ethical governance gate. The ethical governance gate is a central idea in the framework. It ensures that the system does not respond only because a technical threat has been detected. It also checks whether the proposed response is ethical. It checks whether the response is explainable. It checks whether the response is policy compliant. The framework is built around three main pillars. The first pillar is autonomy. Autonomy enables the system to act intelligently within defined limits. The second pillar is adaptability. Adaptability enables the system to learn and adjust to changing threat conditions. The third pillar is accountability. Accountability ensures that decisions are explainable, traceable, and governed. In simple terms, this framework says that healthcare cybersecurity actions should pass through an ethical and governance checkpoint before action is taken. That is the foundation of AAIF. This slide summarizes the literature review for Objectives 1 and 2. For Objective 1, the literature showed that healthcare cybersecurity requires 4 categories of requirements. The first category is functional requirements. These include threat detection, monitoring, response, and security event processing. The second category is ethical requirements. These include patient safety, proportionality, privacy, and human oversight. The third category is governance requirements. These include policy alignment, accountability, auditability, and compliance. The fourth category is resource-aware requirements. These are important because many healthcare institutions operate with limited infrastructure. They may have limited bandwidth. They may have limited cybersecurity capacity. They may also have limited technical resources. For Objective 2, the literature showed that agentic AI, adaptive learning, and AI governance can support the design of more intelligent and accountable cybersecurity systems. However, the gap is that many existing studies treat these elements separately. Some studies focus mainly on technical detection. Some focus mainly on governance. Some focus mainly on ethics. Very few integrate these dimensions into one healthcare cybersecurity framework. Therefore, AAIF was designed to close this gap. It integrates requirements, governance, and agentic AI into one conceptual structure. The key point from this slide is clear. The literature supported the need for a framework that is not only technically intelligent, but also ethically and institutionally accountable. This slide presents the literature review for Objectives 3 and 4. For Objective 3, the literature showed that AI and agent-based architectures can support intrusion detection, anomaly detection, and autonomous response. However, many existing architectures remain reactive or technically focused. They may detect threats, but they do not always explain their decisions. They do not always align actions with healthcare ethics. They do not always follow governance requirements. For Objective 4, the literature showed that simulation is useful for testing cybersecurity systems. Simulation allows researchers to create controlled threat scenarios. It allows system behavior to be tested safely. It also allows performance comparison without risking real systems or real patients. However, the gap is that many simulation studies focus mainly on technical performance. They do not sufficiently test ethical governance, interpretability, and resilience together. Therefore, this study developed AAIF as both an intelligent architecture and a simulation-tested governance-aware framework. The key message is that the framework was not only designed. It was also tested under adversarial and healthcare-oriented conditions. This slide summarizes the literature review for Objectives 5 and 6. For Objective 5, previous studies commonly evaluated AI cybersecurity systems using technical metrics. These include accuracy, precision, recall, F1 score, AUC, and latency. These metrics are important. They show how well a model detects and classifies threats. However, in healthcare, technical performance alone is not enough. A system may be accurate, but it may still fail if it cannot explain its decisions. It may still fail if it violates ethical principles. It may still fail if it acts against institutional policy. Therefore, this study introduced a multi-criteria evaluation approach. This approach included technical performance. It included ethical compliance. It included governance alignment. It included resilience. It included interpretability. It also included human oversight. For Objective 6, the literature showed that validation often relies on benchmark datasets. Benchmark datasets are useful, but many studies do not fully reflect resource-constrained healthcare conditions. Therefore, this study used scenario-based validation to test AAIF under constrained conditions. These included limited bandwidth, CPU pressure, and adversarial stress. In simple terms, the study did not only ask, can AAIF detect threats? It also asked, can AAIF respond safely, ethically, and reliably in a healthcare environment with limited resources? The literature review revealed 6 major research gaps. The first is the ethical gap. Many AI cybersecurity systems lack embedded ethical reasoning. The second is the governance gap. Governance is often treated as an external checklist. It is not always built into the AI system itself. The third is the architectural gap. Many architectures are reactive. Many are opaque. And many are not designed for healthcare-specific cybersecurity needs. The fourth is the simulation gap. Many simulations do not sufficiently reflect healthcare conditions. They also do not fully test governance-aware decision-making. The fifth is the evaluation gap. Most evaluations focus mainly on technical metrics such as accuracy and detection rate. The sixth is the validation gap. Many studies do not validate AI cybersecurity systems under resource-constrained healthcare conditions. These gaps justify the development of AAIF. The research contribution begins from this point. AAIF was developed to integrate technical intelligence, ethical reasoning, governance compliance, interpretability, and resilience into one framework. This study adopted a positivist pragmatist paradigm. The positivist aspect means that the study relied on measurable evidence. For example, the framework was evaluated using metrics such as accuracy, F1 score, AUC, ethical compliance, governance compliance, decision latency, and resilience index. The pragmatist aspect means that the study focused on solving a practical real-world problem. That problem is how to support ethical and resilient cybersecurity in healthcare systems. The study also adopted a deductive approach. This means that it drew from established theories, including agent theory, reinforcement learning, and machine ethics. These theories were then applied to develop and evaluate AAIF. The methodology used was design science research. This was appropriate because the goal was to develop and evaluate an artifact. In this study, the artifact is the Agentic Artificial Intelligence framework. For a non-technical audience, the methodological idea is straightforward. The study identified a practical problem. It designed a solution. It tested the solution. And it evaluated whether the solution addressed the problem. Design science research guided the development and evaluation of AAIF. This methodology was appropriate because the study was not only trying to understand a problem. It was also trying to design a solution. The environment side of the methodology represents the real-world context. This includes healthcare stakeholders, healthcare institutions, cybersecurity risks, and governance needs. The knowledge base represents the theories, frameworks, and standards that inform the study. These include agent theory, reinforcement learning, machine ethics, NIST Cybersecurity Framework 2.0, and HIPAA. The design process followed a clear sequence. First, the problem was identified. Second, the requirements were defined. Third, the framework was designed. Fourth, the architecture was developed. Fifth, the artifact was evaluated. Finally, the results were validated. For a non-technical audience, design science research simply means this: a practical problem was identified. The solution was designed. The solution was tested. And the results were evaluated. That is why this methodology fits the study. This slide presents the data processing and evaluation workflow. The process began with requirement identification and conceptual framework design. After that, the data sources were selected. The study used public benchmark cybersecurity data from CSET 2017, CSC IDS 2018, and Adabara 6.2. The data was then prepared through preprocessing steps. These steps included cleaning, scaling, feature selection, and train test preparation. After preprocessing, the AAIF architecture was developed and tested. The framework was then evaluated using multi-criteria metrics. These included technical metrics, ethical metrics, governance metrics, resilience metrics, and interpretability metrics. Finally, scenario-based validation was conducted in a simulated healthcare environment. This workflow is important because it connects the 6 research objectives to the actual implementation process. In simple terms, this slide shows how the research moved from theory, to data, to framework development, and then to evaluation. It also shows that each objective had a clear methodological role. This study used public benchmark cybersecurity data and a simulated healthcare environment. CSET 2017 was used for intrusion detection benchmarking. CSC IDS 2018 was used for cross-dataset validation. Adabara 6.2 was used for resilience-related evaluation. The healthcare simulation context was inspired by KIU teaching, hospital, and research. An important ethical point must be emphasized. No real patient data was used in this study. No live hospital system was attacked. No live hospital system was tested. The cybersecurity data came from public benchmark sources. The healthcare context was simulated. This made the study safer, more ethical, and reproducible. For the technical audience, the use of multiple data sources helped support robustness and cross-domain evaluation. For the non-technical audience, the simple point is this: the framework was tested in a safe environment that imitated relevant cybersecurity conditions, without exposing real patients or hospitals to risk. This slide presents the model selection and simulation baselines. AAIF was compared with different baseline approaches. These included classical machine learning models, deep learning models, conventional intrusion detection systems, explainable AI systems, and trust-aware rule-based approaches. The purpose was to evaluate whether AAIF could perform better than existing approaches. However, the comparison was not only about technical accuracy. It also considered ethical compliance, governance alignment, resilience, interpretability, and decision latency. This is important because AAIF is not just another detection model. It is a governance-aware cybersecurity framework. Therefore, the question was not only, does AAIF detect threats? The question was also, does AAIF detect and respond in a responsible, explainable, and policy-aligned way? This distinction is important for understanding the contribution of the study. This slide presents the hardware and software environment used for implementation. The hardware environment included an HP EliteBook with an Intel Core i7 processor and 16 GB of RAM. The software environment included Python, Anaconda, and JupyterLab. The study also used several software libraries. These included TensorFlow, scikit-learn, NumPy, Pandas, Keras, GraphViz, and NetworkX. For the technical audience, these tools supported model development, data processing, simulation, and evaluation. For the non-technical audience, the simple point is that the framework was implemented using standard and reproducible research tools. Reproducibility is important. Other researchers should be able to understand the process. They should be able to verify the work. And they should be able to extend it in future studies. Therefore, this environment supported both implementation and research transparency. This is one of the most important methodology slides. AAIF was evaluated using a multi-criteria approach. The technical metrics included accuracy, F1 score, AUC, and latency. This measured how well the framework detected and responded to threats. The ethical metrics included ethical compliance ratio, force escalation, and ethical consistency. This measured whether the framework acted in line with ethical rules. They also measured whether it avoided unnecessary or unsafe escalation. The governance metrics included governance compliance index, auditability, and policy alignment. This measured whether the framework followed governance requirements and produced traceable decisions. The resilience metrics included resilience index 2, recovery, and adaptability. This measured how well the framework could maintain or recover system performance under stress. The interpretability metrics included explainability, transparency, and traceability. Human oversight was also considered through human-in-the-loop escalation. The key message is this: in healthcare cybersecurity, a system must not only be accurate. It must also be safe. It must be explainable. It must be accountable. And it must be resilient. That is why this study used multi-criteria evaluation. This study followed ethical and institutional safeguards. No real patient data was used. Only public benchmark cybersecurity data was used. The framework was tested in a simulated environment. AI actions were constrained by governance logic. Institutional approvals were obtained. These included Kampala International University Research Ethics Committee approval. They also included Uganda National Council for Science and Technology approval. Data handling followed principles of anonymization, secure processing, and restricted use for research purposes. This slide is important because the study is located in healthcare. Healthcare involves sensitive issues of privacy, safety, and institutional responsibility. The ethical position of this study is clear. The research did not expose real patients. It did not expose real hospital systems. And it did not expose real clinical data to risk. Instead, simulation was used to test the framework safely and responsibly. This slide presents the methodological safeguards used in the study. Because the validation was simulation-based, the study used multiple data sources and multiple scenarios. Because there was no live hospital deployment, a KIU teaching hospital and research-inspired healthcare topology was used to provide contextual relevance. Because benchmark cybersecurity data may not fully represent all real-world healthcare conditions, cross-dataset validation was included. Because autonomous AI responses can create risk, the ethical governance gate and human oversight were included. These safeguards help strengthen validity, reproducibility, and ethical control. This point can be explained simply. Every research method has limitations. What matters is whether the researcher recognizes those limitations, and whether the study takes steps to reduce their effect. That is what this study did through methodological safeguards. This slide presents the results for Objective 1. Objective 1 focused on identifying the requirements needed for AAIF. The requirements were grouped into 4 major categories. The first category was functional requirements. These include threat detection, response automation, context-aware monitoring, and security event processing. The second category was ethical requirements. These include patient safety, proportional response, privacy preservation, and human oversight. The third category was governance requirements. These include policy alignment, auditability, regulatory compliance, and accountability. The fourth category was resilience requirements. These include adaptability, recovery, continuity, and robustness under changing conditions. The key finding from Objective 1 is that healthcare cybersecurity requires a framework that integrates all 4 categories. It is not enough to build a system that detects attacks. The system must also respond responsibly. It must comply with policy. It must preserve patient safety. And it must support resilience. This finding provided the foundation for the conceptual framework and architecture developed in the next objectives. Slide 28, Objective 2, Conceptual Framework Design. This slide presents the results for Objective 2. Objective 2 focused on designing the conceptual framework. The framework includes 4 main layers. The first layer is the ethical reasoning layer. This layer supports rules, norms, transparency, and ethical checks. The second layer is the cognitive and decision-making layer. This layer supports reasoning, adaptive learning, policy-aware decision-making, and contextual analysis. The third layer is the agentic behavior layer. This layer supports goal-directed action, autonomy, and human-in-the-loop operation. The fourth layer is the environmental interface layer. This layer connects the framework to network traffic, logs, sensors, devices, and system outputs. The operational flow follows a clear sequence. The system perceives the environment. It reasons about the situation. It checks ethical and governance rules. Then it responds. This sequence is very important. AAIF does not simply react automatically. It first checks whether the action is safe, ethical, explainable, and policy compliant. Returning to the opening hospital scenario, this is where AAIF becomes useful. It does not simply shut down a system because risk has been detected. It first reasons about the context. It checks patient safety. It verifies governance rules. Then it determines the most appropriate response. This slide presents the developed AAIF architecture. The architecture begins with inputs. These inputs include network traffic, device logs, threat intelligence, and patient care context. The perception layer receives and processes these inputs. The reasoning layer analyzes the situation. It assesses risk. It predicts possible threats. The ethical governance gate then checks whether the proposed response is safe, ethical, and compliant. Only after this check does the response action layer execute approved actions. These actions may include alerting, mitigation, isolation, logging, or escalation. The architecture also includes explainability, human oversight, audit logging, and continuous learning. A simple analogy can help explain the architecture. AAIF is like a trained hospital security officer. A good security officer does not only react quickly. The officer observes the situation. The officer assesses the risk. The officer follows hospital policy. The officer avoids harming patients. The officer documents the decision. And when necessary, the officer calls a senior expert. AAIF is designed to provide that kind of responsible intelligence in cybersecurity. That is why the ethical governance gate is central to the architecture. This slide presents the results for Objective 4. Objective 4 tested AAIF under adversarial and cross-domain cybersecurity scenarios. The purpose was to examine whether the framework could remain stable and effective under attack conditions. The simulation considered hostile or abnormal network behavior. It also considered changing threat patterns. And it included health-correlated operational constraints. The study used Thesis 2017 and CIC IDS 2018 to test robustness and generalization. The results showed strong technical performance. AAIF achieved an F1 score above 0.90. It achieved an AUC above 0.98. It maintained a false positive rate below 5%. The baseline resilience index was 0.43. The key finding is that AAIF remained accurate, stable, and resilient under adversarial conditions. For a non-technical audience, the meaning is simple. The framework did not only work when conditions were normal. It also remained reliable when the system was under stress. That is important because real cybersecurity environments are unpredictable. This slide presents the results for Objective 5. Objective 5 evaluated AAIF using technical, ethical, governance, and resilience metrics. From the technical perspective, AAIF achieved an accuracy of 0.97. It achieved an F1 score of 0.95. It also achieved an AUC of 0.98. These results indicate strong detection and classification performance. From the ethical and governance perspective, AAIF achieved ethical compliance of 0.99. It achieved governance compliance of 0.98. It achieved audit completeness of 0.98. It also recorded a false escalation value of 0.00. From the resilience perspective, AAIF achieved a resilience index 2 value of 0.509. It maintained decision latency of approximately 35 milliseconds. It also showed strong recovery stability. The most important point here is balance. AAIF did not only perform well technically. It also maintained ethical compliance. It maintained governance alignment. It maintained auditability. And it supported resilience. This directly supports the central argument of the thesis. Healthcare cybersecurity systems should not be evaluated only by how accurately they detect threats. They should also be evaluated by how responsibly they respond. This slide compares AAIF with other baseline frameworks. The comparison included traditional intrusion detection systems, explainable intrusion detection systems, and trust-aware rule-based systems. AAIF achieved the strongest overall performance across the key evaluation dimensions. It achieved accuracy of 0.97. It achieved an F1 score of 0.95. It achieved ethical compliance of 0.99. It achieved a resilience index 2 value of 0.509. One important observation is that AAIF had slightly higher decision latency than some simpler baseline systems. However, this is an acceptable trade-off. The reason is clear. AAIF does more than classify threats. It also performs ethical checking. It performs governance validation. It supports explainability. And it includes resilience assessment. In healthcare, the fastest decision is not always the best decision. The best decision is one that is fast enough, safe enough, explainable enough, and accountable enough. Therefore, AAIF provides a stronger balance between performance, ethics, governance, and resilience. This slide presents the results for Objective 6. Objective 6 validated AAIF under resource-constrained healthcare conditions. The validation considered bandwidth limitations. It considered CPU pressure. It considered power constraints. It also considered adversarial pressure. The study compared three governance modes. These were the agentic model, the rule-based model, and the black box model. The results showed that AAIF maintained the highest resilience index 2 value within typical clinical bandwidth conditions. Black box models degraded the most under constrained conditions. Rule-based models performed more stably than black box models. However, they were less resilient than AAIF. This result is important because many healthcare environments, especially in low and middle-income countries, operate under resource constraints. A cybersecurity framework for such environments must not assume perfect infrastructure. It must be able to function under pressure. The key message is that AAIF remained robust. It remained governance-aligned. And it remained clinically relevant under constrained healthcare conditions. This slide shows how AAIF aligns with regulatory and governance standards. The perception layer supports the identify and detect functions of NIST Cybersecurity Framework 2.0. The ethical governance gate supports the govern function. The decision engine supports protect and respond. The resilience module supports recover. Data handling controls align with HIPAA security principles. The compliance highlights include governance compliance of approximately 0.98. Ethical compliance was approximately 0.99. Force escalation was 0. Decision latency was approximately 35 milliseconds. The key point is this: AAIF does not treat governance as an external checklist. Instead, governance is built directly into the system's decision-making process. For a non-technical audience, this means the system does not only ask, "Can I act?" It also asks, "Should I act? How should I act? And can I justify the action?" That is the governance value of AAIF. This slide summarizes the findings according to the 6 research objectives. Objective 1: identify the functional, ethical, governance, and resilience requirements. Objective 2: produce the conceptual framework. Objective 3: develop the AAIF architecture. Objective 4: showed that AAIF remained robust under adversarial simulation. Objective 5: demonstrated strong technical, ethical, governance, and resilience performance. Objective 6: confirmed the relevance of AAIF in resource-constrained healthcare environments. Together, the findings show that AAIF is technically effective. It is ethically governed. And it is practically relevant for healthcare cybersecurity resilience. At this point, the central message of the results is clear. Ethical governance improves the trustworthiness of autonomous cybersecurity systems. This is the main contribution of the results chapter. This study concludes that cybersecurity resilience improves when ethical governance is built directly into AI decision-making. AAIF supports governance by design. It enables responsible autonomy through ethical reasoning, adaptive learning, and human oversight. It improves cybersecurity resilience through stronger detection, response, recovery, compliance, and resilience index 2-based evaluation. The simulation-based validation confirmed that AAIF is relevant for resource-constrained healthcare environments. The final message of the study is clear. Healthcare cybersecurity should not only be intelligent. It must also be ethical. It must be accountable. It must be explainable. And it must be resilient. That is the contribution of AAIF. This study makes 5 major contributions. The first is contribution to knowledge. The study advances governance-embedded agentic AI and resilience-oriented cybersecurity evaluation. The second is contribution to practice. AAIF provides a practical framework that can guide healthcare cybersecurity design and implementation. The third is methodological contribution. The study applies design science research, simulation-based development, and multi-criteria evaluation. The fourth is policy and governance contribution. The study operationalizes NIST Cybersecurity Framework 2.0 and HIPAA principles within autonomous cybersecurity decision-making. The fifth is societal contribution. The study supports safer, more accountable, and more trustworthy digital healthcare systems. This is especially important in low and middle-income environments. In summary, the contribution is theoretical, practical, methodological, policy-oriented, and societal. This study aligns with 4 Sustainable Development Goals. It supports Sustainable Development Goal 3, which is good health and well-being. It does this by promoting safer and more resilient digital healthcare systems. It supports Sustainable Development Goal 9, which is industry, innovation, and infrastructure. It does this by advancing agentic AI innovation for healthcare cybersecurity. It supports Sustainable Development Goal 16, which is peace, justice, and strong institutions. It does this by promoting accountability, transparency, and ethical AI governance. It also supports Sustainable Development Goal 17, which is partnerships for the goals. It does this by encouraging collaboration among hospitals, policymakers, regulators, researchers, and technology developers. The broader message is that secure digital healthcare is part of sustainable development. A healthcare system cannot be fully digital and sustainable if it is not secure, trustworthy, and resilient. Like every research study, this work has limitations. The first limitation is that validation was simulation-based. It was not based on live hospital deployment. The second limitation is that benchmark cybersecurity datasets may not fully capture all real clinical and Internet of Medical Things traffic patterns. The third limitation is that the simulation did not fully capture real human-AI interaction in clinical workflows. The fourth limitation is that broader multi-site validation is still needed. However, these limitations do not weaken the value of the study. Instead, they define the next stage of research. They show where AAIF can be extended. They show where it can be tested. And they show where it can be improved in future work. The important point is that this study provides a validated foundation for moving toward real-world deployment. Future work should move AAIF from simulation toward real-world deployment. The first area of future work is pilot testing in real healthcare environments. This would help assess how AAIF performs with live infrastructure, real workflows, and operational constraints. The second area is human-AI interaction. Future research should examine how clinicians, IT staff, and cybersecurity teams understand and supervise AAIF decisions. The third area is adaptive governance. Ethical thresholds and policy rules should be refined over time. This will help reflect changing institutional needs and regulatory expectations. The fourth area is long-term resilience assessment. This would help measure how AAIF affects institutional resilience over longer periods. The fifth area is cross-sector extension. AAIF can be adapted to other critical infrastructure sectors. These include education, finance, energy, and public administration. Finally, research partnerships will be important. They will help translate AAIF from a research framework into operational practice. This study makes recommendations for 5 stakeholder groups. First, healthcare institutions should adopt AAIF through phase deployment and readiness assessment. This means institutions should not deploy such systems abruptly. They should first assess infrastructure. They should assess governance readiness. They should assess staff capacity. And they should assess operational risks. Second, system operators should be trained to interpret, validate, and supervise AI decisions. This is important because human oversight remains essential. Third, policymakers should establish regulatory sandboxes for agentic AI governance. This would allow responsible testing of AI systems under controlled regulatory conditions. Fourth, regulators should translate NIST Cybersecurity Framework 2.0 and AI governance principles into operational standards that healthcare institutions can implement. Fifth, researchers should extend adaptive ethical rule engines and conduct real-world validation. The key recommendation is clear. AAIF should move from simulation toward policy-supported healthcare deployment. This slide presents indexed journal publications produced from the PhD research. The publications cover several related areas. These include agentic AI in cybersecurity, trustworthy agentic AI systems, ethical governance protocols for healthcare cybersecurity, and conceptual framework design. The individual publications will not be read in detail here. The main point is that the PhD research generated scholarly outputs across agentic AI, AI ethics, governance, cybersecurity, and healthcare resilience. These publications also show that the research contributed to ongoing academic conversations beyond the thesis itself. This strengthens the academic visibility, scholarly contribution, and research value of the study. This slide presents additional journal outputs and a preprint from the PhD research. These outputs extend the research into global AI governance, trustworthy cyber defense, and cybersecurity in resource-constrained environments. Together with the publications shown on the previous slide, they show that this research contributes to a broader agenda. That agenda is the development of trustworthy, ethical, and governance-ready AI systems for cybersecurity. The key message is that the thesis is supported by a strong publication record and an active research trajectory. This slide presents conference dissemination from the PhD research. The conference papers focused on agentic AI, national AI governance, cyber resilience, digital entrepreneurship, sustainability, and capacity building. This is important because research should not remain only inside the thesis document. It should also be communicated to academic, professional, institutional, and policy audiences. The conference presentations helped extend the visibility of the research. They also connected the study to wider discussions on digital transformation, governance, innovation, and sustainable development. Therefore, this slide demonstrates that the research has both academic and practical dissemination value. This slide presents manuscripts under review and broader research dissemination activities. The manuscripts under review focus on trustworthy and ethical AI for intrusion detection. They also focus on policy-enforced AAIF architecture. And they address ethical AI governance for healthcare cybersecurity in resource-constrained settings. The slide also shows stakeholder engagement, a co-authored book publication, and cybersecurity seminar facilitation. This demonstrates that the PhD produced more than a thesis. It produced continuing research activity. It produced public engagement. And it produced knowledge dissemination. The broader value is that the work is positioned for future development, collaboration, and real-world impact. This slide presents selected key references used in the study. The references include works on research design, design science research, intelligent agents, AI ethics, NIST Cybersecurity Framework 2.0, HIPAA, OECD AI Principles, WHO AI Ethics, and the European Union AI Act. These sources provided the theoretical foundation of the study. They also supported the methodological, technical, ethical, and governance dimensions of the research. The full reference list is available in the thesis document. This slide is included to show that the research is grounded in established scholarship, recognized cybersecurity standards, and relevant AI governance frameworks. Thank you very much for your attention. In summary, this research developed and validated the Agentic Artificial Intelligence framework for ethical governance and cybersecurity resilience in healthcare systems. The central message is that healthcare cybersecurity should not depend only on technical detection. It should also include ethical governance. It should include accountability. It should include explainability. It should include human oversight. And it should include resilience. Returning to the opening hospital scenario, the question was not only whether a cyber attack could be detected. The deeper question was how an intelligent system should respond safely, ethically, and responsibly in a healthcare environment. AAIF provides a framework for addressing that challenge. The study shows that future healthcare cybersecurity systems should not only ask, can action be taken? They should also ask, should action be taken? How should action be taken? And can the action be explained, audited, and trusted? Thank you once again. Questions, comments, and guidance are welcome.